Hello friends, welcome to our channel. So in this video, we are going to look at today's daily challenge problem 2872, maximum number of k-divisible components. The overall solution will be based on breadth-first search with indegree. So here we have a tree, right? And this is the edge relations, and for each node they have corresponding values. So we want to split the tree into as many possible components as possible, but the requirement is that the sum of those values in each component is a multiple of this k, right? So this is the example 1. So you see there are two components. So if you look at 1 and 3, so you have 1 and 3, so their sum is 12. And if you look at 0 to 4, so this is 0 value, there's 2 value, there's 4 value, so it's 6, right? So similarly, you can look at example 1. So here, before we move forward, there's some constraint for consistency and for problem size constraint. So we are not going to read it through. But I want to come to one hint. So here, this hint is very important. So if a leaf node is not divisible by k, then it must be in the same component as its parent node. So we may merge it with its parent node. So that's the one. And another one is if a leaf node is divisible by k, then it will be in its own components. So we can separate from the parent node. This two actually covers the main point of the logic for this problem. So another one is that the sum of values is divisible by k. At least you have one component. That's also actually very important. So because of this, actually we have this 2 and 3. So with that said, let's look at the main problem statement, main idea and its connection with other problems. So this problem, if we look at BFS with indegree, so actually you can think of Kahn's algorithm. So this problem actually we can see it's essentially Kahn's algorithm, but not for topological sort, right? If you do not know Kahn's algorithm, you can watch the videos for problem 210 and problem 27. So these two problems are requiring us to do topological sort, right? So the nature of this algorithm, Kahn's algorithm, or here BFS with indegree, is essentially multi-source BFS with indegree. But in these two problems, the purpose is for topological sorting. But here, it's also multi-source BFS with indegree, but we count the maximal number of k-divisible components. So with that said, I guess we know the overall idea and the connection of this problem with other problems. So now let's look at the code. So I'm going to explain the code in between, line by line, and then afterwards we're going to give a quick summary. Right? First, I want to treat some edge cases. So if n is less than 2, right? So in this case, we just need to return 1. Because you have only one, if even just one node, right? So it's just return 1. So this is the one. And then we want to build this graph, and also we want to have the indegree information. So build the graph, and also record the indegree. So later we are going to modify the indegree. So we can use dictionary here. So graph. So here's so we have n nodes. So each we can give a set, empty set at the very beginning for I in range n, right? So the indegree. So I0 for I in range n. Originally we set it to be 0. So then we scan or traverse this edges list to build the graph and also update the indegree. So this is super easy. So for AB in edges, right? So graph B is in the neighborhood of A, and also A is in the neighborhood of B. This is a very routine. Symmetrically in parallel, so we indegree of A is incremented by 1, and the indegree of b is incremented by 1. So in a rigorous sense, this is the total degree, not the indegree, because indegree is more precisely used for directed graph, right? But here the graph is undirected or bidirectional, right? So we have this part. Then we get, if you are not familiar with this information, so for example, you can print out a graph, and also you can print out indegree. So just to have an idea, right? For example, this example 1, 0 has neighborhood 2, and 1 has neighborhood 2, 3, and 2 have neighborhood 0, 1, and 4, and 3 has neighborhood 1, and 4 has neighborhood 2. So the indegree, so let's see, did I print? Yeah, so indegree of 0 is 1, right? So 1 is 2, right? You can see the length of the set is 2. And 2 is 3, right? 3 is 1, 4 is 1. So with these two pieces of information, so we are ready. Actually, we will be able to count the k-divisible components. So what shall we do? First, I'm going to initialize as a result variable. So this variable is a counting variable. We're going to update this variable and in between the traversal, and afterwards we are going to return its final state. So then we can get a queue. So this is the source of our collection. So we're going to use BFS. So we use a queue. So here we use DAG in Python. So here we start from the leaf nodes, because the leaf nodes for this problem is special. You can also see the ends too, right? So now this is node for node degree in degree items. If degree equals 1. So this leaf node, then we are going to do the traversal. So when we do the traversal first, we get the current node. Let's Q pop left. So what shall we do? So because there are two possibilities. First, the value corresponds to this node is a multiple of k. So in this case, we don't add the values to the parents or to the neighbor of the node, right? So if it is, so we don't add. If it's not, we should add this value to its neighbor. So what shall we do? So we do a sprite value. So we first set it to be 0, right? If this, then we check the value corresponding to this node. If the value is not a multiple of k, then the spread value will be the value corresponding to this node, because hint 3, right? Yeah. We need to add this value to the neighbor, or you can call it parents, right? So, but it's not very precise. So then, what we want to do, because then we decrement the degree of this node by 1, right? And then we want to check if the values of the current node is a multiple of k. What if it's not, right? If it's not, we are going to update this this value to be the values node. So this actually is the case. First, let's see. We can do like if it is 0, we need to actually increment the result by 1. Otherwise, so we do this. We just reset the spread value. So if you look at this line of code and this line of code, and then you arrive here. So basically it said that if your node has a value which is a multiple of k, and then you form a component. And otherwise, you need to form components with the parent node. But in order to do this, in practice, we add the value of the node to the parents. This is because we need to consider the sum. So up to now, so we checked this node, and then we are going to look at its neighbors. So for node, neighbor in graph node, then if in degree of the node equals 0, then actually we have treated that like here, right? Because if it's a leaf node, and then we are going to decrement the indegree by 1. So in this case, we just continue. Otherwise, so the indegree of this neighbor is going to decrement by 1. The reason we decrement by 1 because we have considered the node, right? So in this case, we are going to add the neighbor value by the spread value, right? Depending on whether the node currently we are looking at has a value that is a multiple or not. So the values can be either 0 or the value of the node, right? So up to here, we finish this part, and then we are going to still check if we need to include some node. So if the current neighbor, the degree is 1, meaning that this is a newly formed a leaf node. You can interpret it like this. Then we are going to append this one. So after we end this queue or this while loop, then the final state of the result is the number of k-divisible components. So we can return the result state. So that's actually the whole solution. Let's first do a test. It's not right. Let's see what's the problem. Let me check that, right? So if n is less than 2, we're going to get this. Yeah. So we set and we do this indegree a b. So this is the correct. And collections deck. Yeah, that's right. So node spread value. If it's we decrement by 1, and then we check, right? So we check if values node is a multiple key. So we're going to do this, and then we otherwise spread value will be values node. This is correct. And then for neighbor in graph node, so if the indegree, so here it's not node, right? It's neighbor. If neighbor is 0, so then we continue. Otherwise, we modify the information for the neighbor. Then we do add neighbor to the queue. Let's check again. Yeah, it passes one example. So now let's look at the generic case. Yeah, it passes all the cases. So here I want to make a comment. So here you may see that the node might have multiple neighbors. So which neighbor? So you add the values. So because here we spread the value, we add values to maybe to many nodes. So here that's not correct interpretation. So it's a for loop here. Essentially, we consider one node, one neighbor. The reason is that the node here is degree 1 node, right? So if the neighbor is already considered, we continue. Otherwise, because it's degree 1, the effective node actually is just 1. So in other words, in effect, we only add the value to one neighbor, right? So this is the crucial part, that is the in degree is 1 when we add to the queue, right? The reason for this is in degree of this node is 1, right? So with that said, I guess we finished the main coding part. So let me give a quick summary. So this problem, so marked hard, but actually it's the code is very routine. So here we used multi-source BFS with in degree to solve it. And the purpose is to find or count the maximum number of k-divisible components. So if you compare the Kahn's algorithm detail for topological sort, so actually this is nothing but Kahn's algorithm essentially. So so that's actually also the overall view for this problem if you first see it. So as a reminder, so you can watch the videos for problem 210 and 207 to practice Kahn's algorithm. So you see you have graph, you have indegree, and then you also modify the indegree so that you can include into the while loop. So with that said, I guess that's the summary, and thank you for watching.